Hi, uh, I'm Dr. Michael Harmon. I'm a professor, associate professor. Um, I'm sorry, I just got promoted. I forgot. I'm now an. No, I am associate. I was assistant. Okay, I'm the middle level. I'm not a full professor yet, but I'm getting there. Uh, I'm uh, I'm the program coordinator for the online Masters of Science in Geographic Information Systems and Spatial Analysis at WVU, and I decided to make a series of videos breaking down some of the most commonly confusing and conceptually difficult topics that we find in GIS. So this applies both to students who are currently learning GIS and some of us more seasoned users who, from time to time, may forget some of the things that we were told to remember when we were in undergraduate studies, for example, or even in graduate school. So one of the things that fits that bill is coordinate reference systems and projections. And so this is a short video to hopefully um, clear up some of that confusion and make the conceptually difficult easier to understand. So this is me standing in front of wonderful Woodburn Hall. Just off to the right out of camera frame is Brooks Hall, and that is where we are headquartered. Like I said before, I'm the program director of the Online Masters in GIS and Spatial Analysis. Here's my contact information and a link to our website. Should you want to check out WVU, Department of Geology and Geography, or if you want to contact me with any questions, be happy to hear from you. Okay, coordinates, reference systems, and projections. So where this tends to cause people to get confused is understanding geographic coordinate systems, just general lat long, and then understanding the projected coordinate systems like the UTM and the state plane, figuring out when and how to reproject data, uh, issues that come up because you're mixing data sets with different coordinate reference systems, distortions, and then the EPSG codes. So we're going to start off with just what is a geographic coordinate system and a projected coordinate system, and why some of this matters. Well, why does it matter? Well, for one, if you're working in a GCS, you have to remember that your units are in angular degrees because degrees, minutes, and seconds of geographic coordinates are all about very precise directional alignments that, when followed to their terminus, um, reach a certain point on the surface of the Earth. And if we're using a GIS, for example, to do something like, oh, I don't know, figuring out how far it is from city A to city B, what we really want to know is the distance between those 2 points, not the angular measure. In this case, like you see here, I've got this triangle where you have that right angle down there at the hypotenuse, and that tells me it's 90 degrees. 90 degrees from, say, Chicago to Washington, D.C. tells me absolutely nothing. And so geographic coordinate systems are just not useful for most all of the things that we want to know. Whereas projected coordinate systems, they've been mathematically fitted or projected onto a 2D plane, and so they measure very differently. They measure in actual numerical distances, like in meters or feet. So let's go back and review a bit. What is a GCS, and how do we get started with one? Well, we're going to start off with this object we call a geoid. And a geoid is the Earth, but it's not like the surface of the ground or the bottom of the ocean. It is, if we took the mass of the Earth and used it to measure sort of the gravity that exists based on the density of materials and the thickness and all that from the center of the Earth, we can get this idea of how strongly or weakly the pull of gravity is in different places. And if we were to map that, it would be this sort of, kind of irregular shape. And the idea with this shape is if the planet wasn't moving and spinning, and all the oceans were all interconnected, and based on the pull of this geoid, it would cause all the water levels to sort of zero out to mean sea level. And that's sort of something that we'll need later on. And so using a geoid, this gravitational based measurement, is actually a pretty good way of doing that. Problem is, all GIS is math. Excuse me. And, well, you can't do math on something that looks like that geoid. You just can't. But you can on a perfect mathematical shape like a specific ellipsoid like we see here in the center. But that ellipsoid doesn't exactly look like that geoid. In fact, if you look to the third image, I've got them lined up, and I'm representing the center of each object by the white circle in the middle. And you can see that some places, yeah, it lines up pretty good. Other places, it's off a bunch, either positively or negatively, but it's still not lining up really well. If we're going to have a geographic coordinate system, the first thing that we really have to do is create a datum. Now, a datum is quite simply, it is just a specific ellipsoid, in this case the same one we had on the last page, and the information that we need to move it or position it relative to the geoid. Now we can do this to try to fit it to everywhere or just to a certain location. So I've got 3 arrows here, and I want to point out to the arrow on the left. That is the sort of like the target part of the Earth that we're trying to create a datum for. And so we're going to fit that specific ellipsoid to that part of the geoid. And you see there, it's a relatively reasonable fit. Okay? But in order to do that, we have to move that center of that whole thing. And so now before we had 1 circle in the middle, little white circles, we now got 2 because the 1 has shifted. And this is a datum that, for example, is built and designed for a specific part of the Earth, not for everywhere. As you'll notice by the arrow on the right indicating that in areas where a datum is not designed for, it can be wildly inaccurate. And of course the arrow on the bottom pointing up indicating that the 2 centers no longer are aligned directly on top of one another, but some shift has been applied in order to align the datum, or the ellipsoid to the geoid. And that is what we have to create a datum. What is a datum? A datum is a specific ellipsoid, and we define that based on the length of its major and minor axis. So think the axis pole to pole, and you think of the axis across the middle along like the equator from one side to the other. Those 2 numbers define that shape. So if we take those 2 numbers to specifically identify that ellipsoid, all we have to do then is just in some way indicate how we moved it to make it line up the way we want it to line up. And once we do that, we have a datum. And what makes a datum special? Well, a datum is still just an ellipsoid, but it's one that we can do stuff with. And what's the stuff we're going to do? We're going to create a geographic coordinate system. With a GCS, what we're going to do is create a network of lines of longitude and latitude on that perfect mathematical shape, that ellipsoid that has been fit to the geoid, or what we like to call the datum. And so once we apply those lines of longitude and latitude to that datum, and then reference, those lines to the specific locations where we want them to be, things like the central meridian and the equator, that kind of stuff, we now have a geographic coordinate system. And with a geographic coordinate system, we can go out from the center of the Earth and measure angularly up or angularly down, or in a circle how many degrees around, and identify any spot on the surface of the Earth exactly. But again, that doesn't help us with measuring areas or lengths, and so we have to convert that into a flat 2-dimensional map or a projected coordinate system, which would be more like what you would see here on the right. So what are the pros of a GCS? Well, it works anywhere on Earth. You don't need to choose any zones or any sort of local projections. It's a relatively simple storage. It uses longitude and latitude, and they're measured in degrees, so it's not complex. It's relatively easy to understand. It's really good for exchanging data with other people. It's great for navigation, because with navigation you're really talking about bearings, like so many degrees off of this or so many degrees off of that. In which case, the angular degrees that we have with with a GCS work pretty well. What are the cons? Well, there's no linear units, so you're going to be in degrees, not meters or feet, so it makes it really hard to measure distance and area. There's also distortion of shape and size. Degrees of longitude represent different distances depending on the latitude that you measure them at, because those lines get closer together as you near the poles. And so a difference of 6 degrees in one location and a difference of 6 degrees in another location is not the same 6 degrees. And so it's not like you can have a real simple math equation to make all that stuff work out. The math equation is literally tied to the exact location where you're applying it, and that makes it complicated. It's also really poor for analysis. Things like buffers and density calculations and just about every kind of spatial analysis that anyone has ever imagined will not work with a GCS. It's just going to cause problems, and so you end up needing to project all that data first. And then from a performance issue, even if you're looking at things like on the fly projection, which is a means of letting the software create a reprojected visualization without actually changing the data. That can be and is a complicated process to do that. And when you're in a GCS as opposed to a different PCS, that can start to really slow down the processing speed of your particular hardware when you're dealing with large data sets in GIS. Now, the PCS, on the other hand, it's in linear units, which is good because now we can measure stuff and do things. The distortion is minimal locally. So within the zone or area that it's designed for, it's reasonably small and doesn't generally cause problems. Beyond that, you can also select which type of projected coordinate system you want, because projected coordinate systems preserve some things and it's always at the expense of others. So if you select a particular projected coordinate system that preserves the thing that you're interested in, maybe it's the area, maybe it's the shape, maybe it's the distance, if you preserve the thing that you're interested in, some of the other variables are going to be distorted, but the thing that you're interested in won't be. And so that's good. PCS are 100% better for analysis. They're ideal for all kinds of spatial stuff like buffering and overlays and raster analysis. And they run off of a basic Cartesian grid, uses XY coordinates. They are much, much easier for computers to process and to generate visualizations from. Now, what are the cons? Well, every PCS is region specific and accuracy is optimized only for the area the projection was designed for, and once you get outside that area, it's not going to be as accurate, and the further you get outside the area, the progressively less accurate it's going to be until it gets just downright obtuse. The projection choice can be confusing. A lot of times students struggle to pick the right PCS. Should I be in UTM? Should I be in state plane? Should I generate and create my own custom projections? These are questions that, if you don't do very often, can be difficult to sort of figure out. And then last, how do we deal with the distortion, the trade-off? Well, no single projection preserves everything. Some distort area, some distort shape. You've just got to decide what it is what you need to be the most accurate, and then pick projections that don't distort those things. There's also an extra step. Data often needs to be reprojected from the GCS, and a lot of times students don't do it because the on-the-fly projection makes them think it's already projected when it's not, or they do it incorrectly because they haven't done it very often, in which case then that messes everything up too. Excuse me. So this leads us to the UTM system, the state plane system, and just kind of generally understanding what they are and how they work. So FYI, one projection, ergo a UTM zone, will not work equally well everywhere. Each zone is optimized for its own region. Outside of the intended area, distortions get a lot worse. Now, what we can do is think about the shape and the orientation of a target, of the thing that we're trying to map, the thing we want to look at, because that affects which projection is used. whether we use something like a Lambo conformal conic or some sort of a transverse Mercator like the UTM. So if you're looking at something that is much wider, say east to west, than it is north to south, you probably want to be in some sort of a conic or cone developable surface-based projected coordinate system, something like Lambert conformal conic. Whereas if you have something that's taller north to south than it is wide, like maybe say like the state of Illinois or something, then you would probably want to be in a UTM type system as opposed to Lambert conformal conic. Another thing that causes issues is false easting and false northing, and students just have to remember that the only thing that's going on there is a collective lump sum value added into the coordinate system so that you don't end up with negative numbers ever, because when you're recording data manually or transcribing it or doing something like that, it is so easy to forget to put a negative sign and a minus sign somewhere. And if you don't do that, it can literally throw your data point out into the middle of the ocean or into the other polar hemisphere, if you will, going from like the northern half of the globe to the southern half, because you simply forgot to put a negative sign in. So false easting and false northing adds to those values so that you never have to worry about that. It's also super important that you never disregard datums. When you're using a state plane or UTM, some could be in NAD 27, some could be in NAD 83. Datums are different, but the same coordinates will be in different locations. So if you have one datum that's in UTM NAD 27 and one that's in UTM NAD 83, and you have a particular numeric set of coordinates, and you put those coordinates in each of those data sets, they're going to be different places because the datum is different, and the datum is what we draw those lines of longitude and latitude on, which are the basis for the PCS. Don't automatically believe that the state plane is always better than the UTM or vice versa. You have to think about the area. You have to think about the analysis that you're doing, and you think about the distortions and trade-offs that occur because of that. And although data may look aligned in the map, because most softwares have that on-the-fly stuff, while analyzing stuff like doing measurements of distances and areas or overlays, they can still be wrong if the data doesn't share the same projection and really have like true actual units. Stuff will come out that's not right because everything looked okay when it wasn't. So remember that within state plane zones there's still small distortions, and none of these things are absolutely perfect. But if you're like in a state plane zone, within that zone, distortions should be minimal and shouldn't cause you any real issues locally. But that doesn't necessarily mean that still the state plane is the better option. What if you're looking at something in the northern part of West Virginia, so you want to use the state plane north? You think, that's what I'm going to do. But you're also looking at data that's in the southern part of the state. You want to visualize it all together. Well, you're going to incur extra distortions in the southern half of the state if you use state plane north. Perhaps UTM, like UTM Zone 17N, would be a better option. Whatever you choose, just try to remember that you want to get a PCS that minimizes the distortion that you're interested in and that fits the entirety of your target area as much as possible. So that brings us to the next question: when and how do we reproject data? So first cardinal rule number 1 of spatial analysis: never do anything on unprojected data, period. You want to make sure all your data are in the same projected coordinate system. If you're in different PCSs, that creates a whole slew of mathematical difficulties that can be avoided simply by not doing that. So choose a PCS that's ideal for your location and the analysis that you're doing, and then put everything into that coordinate system. If data is missing a spatial reference, which does happen sometimes, in other words, it doesn't have any listed GCS or PCS, The first thing you have to do is figure out what it is. How do you do that? You read the metadata, you go back to where you downloaded the data and see if it says anything there. You can load the data up and see if it aligns, and if it does, that can sometimes help you figure out what it is. And once you figure it out, next then comes the really fun part. You get to use a tool called Define the Projection. And you can use that to change the label of the coordinate system. That's all it does. Think of your coordinate system as like kind of a dry erase board. The Define the Projection tool is a brand new dry erase marker and an eraser. And it goes up to where it doesn't say anything and you write down what it is. Or if it's incorrect, you erase it and write down what it's supposed to be, what it is correctly. Now all this is great, but if you're trying to change the projection, this is all just the groundworks for that. You cannot use the Define Projection tool to change the coordinate system. You can only use it to correct the label or fill out the label if it's incomplete or absent. Once you do that, then you can use the right tool. And for example, in ARC Pro, that's the Project, or if it's a raster, the Project Raster tool. And that's the tool that will reproject the data using the proper information to generate a new data set in the coordinate system that you want. Now, mixing data with different coordinate reference systems. It's fine to do this if you're just viewing stuff. If you're just looking at data to see what it has, where it is, what it shows, what are the attributes, that kind of stuff, this is fine. I mean, frankly, if that's all you're doing, it doesn't matter if it's in a GCS or a PCS or which one, because the on-the-fly projection will line stuff up within your data frame of your map so that you can see it in the proper context, but it doesn't correct any of the issues of being in a different CRS. But as long as you're just looking at stuff, that's fine. The moment you go into the part of modeling, of analyzing, or doing any of that sort of stuff, making maps, that's where you need to get into the habit of only working in one CRS at a time. So use your skills to figure out the best CRS for the location you're working on and the analysis that you're doing, and put all your data into that coordinate system, and then proceed. Talking about distortions, GCS, it's not really a projection, but distances, areas are distorted because degrees are not constant in size, and it creates issues. We have some projections that are called conformal ones. These are things like Mercator and State Plane. They preserve shape locally, but they distort area or size. We also have some that are called equal area. These would be ones like Albers and Mollyweed. They preserve area, but they distort shape. Then there's the equidistant ones, like the azimuthal equidistance. They preserve distance along certain lines or from a certain point, but they distort shape and area. And there's azimuthal planar, which preserves direction and distorts area and shapes away from the center. Now, we need to remember that PCSs are designed for certain regions. And as long as you're within the region that it's designed for, the distortions are small and minuscule, and for most applications, irrelevant. But each projection uses standard lines or points, things like central meridians or standard parallels. These things in that developable surface model, they touch the sort of surface of the globe when you're doing the projection, if you will. And along these features, the distortion is minimized greatly. In fact, you could almost go as far as to say that along your central meridian and your standard parallels, there's no error to speak of at all. Again, we select projections based on the shape of the area. North, south, or east, west will narrow you down to things like conformal conic or UTMs. Where distortion is least is in that central area along the meridian or along the standard parallels if you're in something like a Lambert conformal conic. Some are secant, some are tangent. That has to do with the number of standard parallels. Where is the distortion the worst? Along the edges, man. When you get out towards the edge of the zone, that is the least accurate part of the zone. But when you take one step further and you're outside the zone, it's even worse. And every step that you go progressively from there, it gets worse. See, what's really happening here is our distortions are basically zero at the standard parallel and at the central meridian. So along those lines, you basically have zero distortion. As you move away from that, you have some. The bounds, if you will, of the coordinate system are kind of that threshold for where, okay, once you go past this, these distortions are going to start to become a problem. Inside, you're going to be okay. Outside, you're not. EPSG codes. Um, this is one of those acronyms that has something to do with petroleum, and it's something out of, I think, Great Britain. Um, I like to think of it like it's the ESP codes, not the EPSG codes. And what it does is it kind of reads your mind. And when your mind is saying, I want it, and you imagine a number here, like we'll say 0001, then there's a whole bunch of stuff that will be associated with that number. That's really all the EPSG codes are. It's a standardized way to reference a CRS so that you don't have to write out this long definition. Because what happens is you might mistakenly call something NAD 27 when it's NAD 83. Or you might not tell us either way and just say, oh, it's the UTM, Zone 17 North. Okay, but if I don't know the datum, I can't, I can't tell you what that is exactly. Instead of writing out those long descriptive titles, the EPSG code is simply like a definition or a recipe. It says this number indicates, and then it tells you all those specific things that you would normally label out longhand if you weren't using an EPSG code. Common student confusion revolves around thinking that the codes are interchangeable labels instead of precise definitions. They're not interchangeable labels. It is a coded definition that just explains everything. Specifically, the exact CRS definition includes the datum, the coordinate system, and any of the projection details. So I think that wraps up this topic, hopefully pretty nice. Apologize for the coughing, but you got to work when you can, and sometimes it's when you're recovering from a upper respiratory infection. So nonetheless, I hope it's been helpful. I hope it's been useful, and I hope that I didn't cause too much distress to anyone's eardrums with my hacking and coughing. But if you are thinking about your geospatial knowledge and your skills, and you're thinking of ways that you might want to look to improve or advance, then maybe you're thinking about an online master's degree. Well, we offer one here at West Virginia University. It's fully asynchronous. It's pretty affordable. It's nationally recognized, and it's available to pretty much people everywhere. We do have virtual information sessions about the degree program that we hold typically 3 in the fall, 3 in the spring, and sometimes 1 or 2 in the summer. So if you're looking into this, don't wait another day. Start checking out and finding out what's best for you. Hopefully it's us, but if not, hopefully you'll find another place that suits you even better. But if you want to learn more about what we're doing in our program, check us out at this link, and hopefully we'll see you in class.